Uh, we consider now and discuss the differential linear momentum equation, in which we look at the Cauchy's equation. The central core equations of fluid dynamics, although there are many equations that we come across, all of them are equally important, but 3 or 4 equations are really the core equations that play a dominant role in all aspects of fluid dynamics. And they are the continuity equation, the law of conservation of momentum equation, the what we call as Navier-Stokes equation. The solution of these reflects or depict or can depict the flow field in totality and normally. But they have many aspects, there are many assumptions, many conditions attached to them, and the Navier-Stokes equations are nonlinear equations that are not easy to solve analytically, and there are some solutions, there are some conditions that under certain restrictions we can have complete analytical solution to them, but complete analytical solution of a full equation of motion of Navier-Stokes, what we call as Navier-Stokes equation, is not available till today. However, in that direction, so as I said, there are 2-3 equations that are very important, and we have to consider them all of them put together. One of them is continuity equation that we have discussed. The other is momentum equation, and then we move on to the Navier-Stokes equation. And one of the important equation in this respect is what we call as Cauchy's equation. We try to derive it in 2-3 ways. And in this respect, we need to remember that if we consider a small control volume, then from Reynolds transport theorem, we arrived at this equation that we have to sum up all the forces when we were considering the Newton's second law of motion. F is equal to ma, force is equal to mass into acceleration of the fluid. So for F, we have to consider all the forces that are occurring, and for ma, we have to consider the fluid flow that is taking place in a real fluid with a mass m and its acceleration. So when we consider that, we will have the role of the velocity and the density and the forces and all of them put together. And the forces that are acting, then according to this Newton's law, we have to equate all the forces to the equation what we call as mass into acceleration. Normally, in a fluid flow field that we come across, the forces that are important or they play a dominant role are either the body forces or the surface forces. From body forces, it's normally the gravitational forces that play an important role. And from surface forces, when there is a viscous flow, shear is introduced, and due to shear, then there are stress forces, there are strain forces, and these are the body forces part, and this is the surface forces part. We add them together, and that in totality will give us the sum of the forces. And of course, we have not considered here the forces like the magnetic forces and so on, but these are the two main that we come across in the real flow field in most of the time, in most cases. And on the right hand side is the flow field, the velocity and the acceleration that played all together in the control volume and control surface volume. So if we consider a small control volume, then we see that for the positive components of the stress tensor sigma ij reflects 9 components of stress in ij direction, where I runs from 1 to 3 and j also runs from 1 to 3. So it will be sigma 1 1, sigma 1 2, sigma 1 3, and similarly there will be sigma 2 1, sigma 2 2, sigma 2 3. Here I have written 1 1 or something, but this is when we are writing in the tensor form. But when we are considering the rectangular coordinates as are shown here, you can see that this is along x, and therefore this is a small infinitesimal distance dx. This is in the y direction, small distance dy, and so this is a small distance dz in the z direction, which is perpendicular to the plane of this screen that you see. So these are 3 mutually perpendicular rectangular coordinates, x, y, z, and we have the stress forces acting in all 3 faces of this small cube that we see here. And so their components act in the left and the bottom and the back faces in the active, but altogether there will be 9. So instead, when I am writing the same things in rectangular coordinates, I will be writing them in sigma xx, sigma xy, sigma xz, and similarly sigma yx, sigma yy, sigma yz, and so on. And as you understand that there are partial derivatives involved there. So we discussed this earlier when we were discussing the momentum equation. So the same equation, we try to derive this Cauchy equation by using the divergence theorem. And you will recall that Gauss's divergence theorem is very well known in the vector calculus because it relates the volume integral and the surface integral. So we can convert the volume integral into surface integral or vice versa. And therefore that helps us to combine terms and to simplify our equations. And we look at the same equation, that the sum of the forces must be equal to the motion that is taking place, that is mass into acceleration. And when we see that, then we obtain, you can see that these are the body forces, the surface forces, the velocity, and beta is the momentum flux correction factor that we discussed, you will recall, when we were talking about Reynolds transport formula. The divergence theorem is, of course, generally written as this, and the divergence of a general vector G over the volume V is equals to the surface area A and the same vector G dot n, where n is a unit vector normal to the surface. So this is the extended form, and this is the divergence theorem that we use to simplify the equation that we have just written above to determine what we were saying at this time, that the Cauchy's equation that we want to derive. And in that equation, if we try to replace the second order tensor by using this equation and conversion, then, and we will try to simplify this equation. The terms are indicated already, that this is body forces, the surface forces. On the right hand side is, this is the velocity, the fluid, momentum of the fluid that is going out minus the momentum that is the fluid that is moving in. The difference of the two will give us the rate of change of momentum. Beta, as we have said, is the flux correction factor. and so on. So from this we shall obtain the Cauchy's differential equation of the linear momentum equation. It applies to any type of fluid field.